Lesson 3, Applications. First application that we're going to look at is something called exponential decay. A radioactive substance decays at a rate that is proportional to the amount of the substance that is present. So the more that's present, the more it decays. Here's a formula that we can use to help us calculate exponential decay. XO is the amount that was originally present in the sample. X is the amount left. T is the time that's gone by. And H is something called half-life. Remember, we've talked about half-life before. Half-life is the amount of time that has to pass for there to be half the sample left. Let's look at an example. The half-life of a certain radioactive substance is 4.5 days. How much of a 123 milligram sample of the substance will be left after 7 days? So we need to use that half-life equation, which was X equals XO, 2 to the power of negative T over H. We're looking for how much is left, so we're looking for X. XO is how much we started with, so in this case 123 milligrams. 2 to the power of negative, T is the time that's passed, so 7 days, over the half-life, which in this case is 4.5 days. Now it's a matter of using your calculator to plug this in. Plug it in and solve it, and you should end up with about 41.8 milligrams left. Part B says how long will it be until there are only 15 milligrams of the substance. So in this case, we know X is 15. We still have 123 milligrams to start. What we're looking for this time is the amount of time, T. Our half-life has not changed, so it's still 4.5. Whenever we have our variable in the exponent, we're going to end up needing to use logs to help us solve it. So the first step is to divide by 123. Since it doesn't go evenly into 15, I'm just going to leave it as a fraction because I want my answer to be as accurate as possible. The next step is to take the log of both sides. So I have the log of 15 over 123 equals, and on the other side I'm going to bring that exponent out front, so negative T over 4.5 times the log of 2. On the right-hand side, I can write that single logarithm as two subtraction ones. So it's log of 15 minus the log of 123 equals negative T over 4.5 log 2. Let's first of all, multiply by 4.5 to get rid of that in the bottom. Will give me 4.5 times the log of 15 minus log 123 equals negative T log 2. Sorry, not tog 2, log 2. To get T by itself, I'm going to divide both sides by negative log 2. And I end up with 4.5 times the log of 15 minus log 123 all over negative log 2 equals T. That's the most accurate expression that I can have. I can now substitute that into my calculator and end up with T being approximately equal to 13.66 days. The next type of application that we're looking at is something called exponential growth. So given ideal conditions, populations of a colony of bacteria, rabbits or humans, will experience exponential growth. So if NO represents the initial population, then the population N after a time period T will be given by the function N equals NO times 2 to the power of KT. K has to be bigger than 0. K is a constant that depends on the colony being studied, so it varies from question to question. The population of a city was 1,115 on January 1st, 1990, and 130,000 on January 1st, 1995. Assuming exponential growth, what was its population on January 1st, 2000? In this question, we don't know that constant k, and so we need to start by figuring that out. If we substitute into our exponential growth equation, we know two different populations, and we know the dates that those arrived on. So I know that I ended up with a population of 130,000, starting with a population of 115,000. 2 to the power, I don't know k, but I do know that the population grew that much in a period of 5 years. So t will be 5. I now need to solve this equation for k. So I'm going to divide both sides by the 115,000 and take the log of both sides. So I end up with log of 130,000 divided by 115,000 equals the log of 2 to the power of 5k. I can write the left-hand side as a subtraction. So the log of 130,000 minus the log of 115,000 is equal to, and on the right-hand side, I'm going to bring that exponent out front, times the log 2. Next step, to get k by itself, I need to divide both sides by 5 log 2. So I end up with the log of 130,000 minus the log of 115,000 divided by 5 log 2 equals my constant k. K, when we plug it into our calculator, works out to be 0.03353755524. Because I'm going to use this in calculations, I want to keep as many decimal places as possible. The question asks us, what is the population in January 1st, 2000? So now that I have my constant, I can substitute into my population growth equation. I'm looking for my new population. I know that it started at 115,000. 2 to the power of my k value is that 0.03537555524. And I have a period of 10 years from 1990 to 2000. Let's get just a little more room. Using your calculator to help you figure it out, you will find that the population is about 146,956 people. Part B asks us for when will the population be 200,000. So we know then that our n will be 200,000. Our initial population was still 115,000. We have 2 to the power of our k value. So 353755524 times the amount of time that goes past, and we're looking for that amount of time. So again, we're going to end up needing to use logs. So divide by this 115,000 on both sides, and then we're going to take the log of both sides. So I have the log of 200,000 over 115,000 equals that decimal number t times the log 2, so I move that exponent out front. You should be familiar with this process now. We're going to write the left-hand side as a subtraction of those two. So I end up with log of 200,000 minus the log of 115,000 equals that big long decimal number times t log 2. On this right-hand side, I actually want to divide by this decimal number and the log 2. So if I do that at this point, I end up with that decimal number log 2 in the bottom. That gives me the expression for t. Substituting in, we end up with t being 22.57 years later. The last application that we're looking at is something called compound interest. So if an initial amount of money, P, is deposited into an account paying an annual interest rate of R, compounded n times a year for a period of t years, then the amount of money in the account after this time is given by the function A equals P times 1 plus R over n to the nt. We need to remember to use the interest as a decimal. Okay, looking at an application. So what this means is that when you deposit money into a bank account, they don't just pay you interest on your $10,000. The first year they do that, if it was compounded annually, but then the next year you get interest not only on your initial investment, but on the interest that you earned previously. So this is just a straight substitution into our compound interest formula. So we're depositing $10,000, so that's the P value, or our principal, times 1 plus, our interest rate is 12%, so it becomes decimal 12, over the number of times a year that the interest is paid. Because it's paid semi-annually, it means that it's paid twice a year. And our exponent is is n again, twice a year times the number of years, which is 25. This is just an exercise in using your calculator and some simplifying. So if I simplify before sticking it into my calculator, I end up with 1 plus decimal 06 all to the power of 50. Or the amount is equal to 10,000 times 1.06 to the power of 50. Substituting into my calculator, I end up with $184,201.54 after 24 years.